So now that we talked a little bit about what atomicity is in general, we're going to skip over the concept of volatile for the moment and just focus on atomic classes and operations because that's what your assignment deals with. And so I'm going to talk about how Java's atomic classes and the operations that it provides allow concurrent programs to use lock-free, thread-safe mechanisms to read and write to single variables, and also to do some really clever computations atomically. And we'll give a couple of known uses of atomic operations, both of which I've talked about already, so we can be fast through that. There's a whole bunch of different atomic classes in the Java util concurrent atomic package. There's atomic variables, which give you this lock-free, thread-safe operations on single variables. So, for example, atomic long supports atomic compare and swap operations called compare and set. We'll talk about that. There's something called long adder, which allows multiple threads to update a common sum efficiently, even if it's highly contended. We're not going to talk a lot about that. Let's talk about atomic operations. So, atomic operations in Java are implemented using hardware, and they're wrapped up by the unsafe class that we talked about a second ago. And this is all really done in the bowels of the platform, in the virtual machine, system libraries, operating system kernel, and the hardware level. So here's compare and swap. This is kind of the granddaddy of them all. This is the heart of synchronization. And I'm going to show you an example here that's not specifically what is happening in your operating system platform or your Java platform. This is sort of logically what's happening. Actually, what's happening under the hood most likely is it's calling a hardware instruction that does something along these lines. But this is, you can think about it in these terms. So the purpose of compare and swap is to atomically compare the current contents of a memory location to a given value. And if and only if they're the same, it'll modify the contents of that memory location to a given new value and return the old value. That seems like an awfully long-winded way of explaining things, but it's actually very concise. So let's take a look. The first thing that this means is that compare and swap is going to run atomically. Now, I've written this, sort of in a C-like manner to emphasize its low-level nature. So here is the memory location, here's the expected value, here's the updated value, and the whole thing here from start atomic to end atomic will all be done in one fell swoop. So, again, this is sort of pseudocode, if you will, but the idea is that however this is implemented, it's typically implemented in hardware, probably with VHDL or whatnot. This set of steps is done atomically. And what does that mean? It means all or nothing. So the first thing we do is we go and we read the contents of the location in memory. This is just a pointer. This is good old C++ pointer. And we store the contents in old value. And then we check to see if the old value, or really the current value, is equal to the value that we expect or that we desire. So that's what we're doing. We compare the current contents of memory, that's what old value is, to a given value. That's what expected is. So we check and say, is the current value at this location equal to what we expect or what we want it to be? And if it is, and only if it is, because it's an if statement, of course, then we're going to update the memory location at that address to the updated value. But if it's not equal, nothing happens. Well, something happens, but not anything interesting happens from the point of view of a side effect. So if they are the same, then the contents of that memory location are modified to the given new value. And no matter what happens, whether we did an update or not, we are returning old value or original value. So we store the old value, check to see if the old value equaled the expected value. If it does, we update the location to the new value, the updated value, and we always return the old value. And all that stuff takes place atomically. And of course, you don't have to worry about this. It's done in the hardware. If there are bugs in the hardware, life as we know it comes to a screeching halt because everything in the world is based on this working. Okay, so armed with those very simple, very low-level semantics, we can then implement a spin lock. And this is a very simple spin lock. This is even simpler than your spin lock, but it's basically the same idea. So what you do is you pass it a pointer to an int, and you have a lock method. And the lock method uses compare and swap, that method we just looked at, to implement mutual exclusion with a spin lock. And here's what it does. It checks to see if the location pointed to by mutex, so mutex is just a pointer, it's going to check to see if that value is 0. That's the expected value. And if the value is 0, and 0 means unlocked or available. So if the value is 0, then we want it to be atomically set to 1, which means true. So what we're basically saying here is, while we are unable to make this work, while the thing is locked, keep spinning, trying to set the value of 0 to the value of 1. That's what that means semantically. And every time compare and swap returns 1, we continue. Actually, wait a second, hold on. Yes, exactly, this is correct. So when the lock is in use, the value of that location is set to 1, which means it's in use. When it's available, it's 0, which means we can get it. So if every time we call compare and swap, saying if it's 0, set it to 1, and it returns 1, that means somebody already holds it. And so we have to just sit there in a busy wait, spinning, 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 spinning. So that's what's called a spin lock. When it is 0, that means someone has released it, and then when we atomically set it to 1, it'll return the old value, which will be 0. So this loop stops when the return value equals 0. And here's what the unlock method does. The unlock method will atomically reset the value to 0, and it does that with some kind of atomic magic, which we're not thinking about here. It's just done in the hardware somehow. And all it does there is it goes to that location pointed to by the parameter and sets its value to 0. And of course, we're assuming that that value is done atomically. We can set to 0 atomically. So notice that that'll set it to 0, and that means that whoever's spinning in this lock will get back a 0 instead of a 1, and we will have atomically locked it. Okay, any questions about that? Very, very, very low-level stuff, but that's what everything is based on. There's also another method called test and set, which is similar to compare and swap. The main difference being test and set doesn't give you the ability to set it to some arbitrary value. It just goes back to 1. So it's sort of like compare and swap, but it's limited to 0 and 1. So what happens here, we have an atomic region, and we just set it, we store the old value, and we then set the value to 1, and then we return the old value, and if it had been 0, then we know that we acquired the lock. So same basic idea, just not as generalizable. So compare and swap is a more generalizable solution than test and set, and for that reason, most hardware nowadays comes with compare and swap, and so that's what we're going to be using throughout the discussions. And this capacity to set the value to something other than 1, every time you do a test and set for compare and swap, is heavily used in the Java atomic classes, as you'll see. What are some somewhat whimsical examples of human-known uses of atomic operations? Obviously, the Star Trek transporter would be one, where you beam people around. Everybody's favorite way to beat traffic gridlock in major cities is transporter beam. Not necessarily going to work anytime soon, but that would be great if you could do it. Clearly, this has to take place atomically. You either have to all show up or none of you show up, not half and half, otherwise you get bad results. And of course, anybody who's a Harry Potter fan rather than the Star Trek fan is probably familiar with the concept of apparition, where you can focus on sort of transporting yourself mentally from one place to another. And if you do it wrong, then bad things happen. So if you go back and read, I think it might be Order of the Phoenix, I forget which book it is, but they learn how to apparate, and they keep like splinching, and pieces of their bodies get left behind, and it's very painful. Okay, so that's the end of the overview of this concept.